starting the stream right now. So that should be on in a few seconds. All right, let's see. I need to get back to Joplin because I wrote some notes in Joplin. There we go. Alrighty. Here's Joplin. Alright. Yeah, caffeine is interesting. Black coffee actually has a lot more caffeine, even compared to the same volume of Mountain Dew. But Mountain Dew has, the sugar, unless you go for the sugarless, Mountain Dew. But I don't do Mountain Dew. Yeah, no pun intended. All right, so streaming is on, and it is time to start the class. So what we are doing today is kind of summarized here. The first thing we're going to do is to talk about pointers a little bit, and how to access a pointer as a parameter in a function. And we'll talk about how to call the function as well. All of that is already introduced in the previous class. So the only thing that is kind of new to this is how we access what a pointer is pointing to, in addition to what we talked about on Tuesday, which is how we access a parameter from the perspective of the callee, how to return a value, and also how to call a function from the caller's perspective. So and to get this done, we'll probably have to talk about what a local variable is, just because otherwise, what are we going to pass a pointer? What is this pointer pointing to? That becomes the next question. So there we have it. So after that, we can get back into compiling C code to TTPSM, and you can see how we compile C code to C code, compile C code to C code, compile C code to C code, and then finally we compile C code to TTPSM. So the process is a little bit interesting because until the very, very last step, okay, all you need to know is C. Now, when I say C, I mean C and C++, because once again, C is a subset of C++, but we know that already in this class. All right, so let's go ahead and get started with this particular sample program. And the way I'm going to do this is to use Online GDB. So Online GDB, I think, is really a great tool, just because you don't need to have your own compiler. It is web-based, and it even let you save your files without having to pay a penny. So I think that's great. All right, so we're gonna introduce this function. It's post increment, which is the same thing as something plus plus. But in order to do this in C and not C++, we have to pass it by a pointer. So here's a pointer. I'll just call it Ptr because it's the only pointer in this particular case. So there's no need to differentiate, what is it a pointer to. Okay, that's the only pointer, which is the only parameter also in this case. So the first thing we do is we say whatever pointer points to is whatever pointer points to plus 1. And then what we will return is whatever pointer points to minus 1, because that's the whole idea of post increment, is the operator as a post increment is supposed to return the value of the very same thing that is supposed to increment, but before the increment. So that's why it's called a post increment operation. And I'm trying to see if anyone has any questions about this. Nope. Okay. Excellent. So we're gonna have a local variable here. Unless it is necessary, I think it is probably a good idea to avoid the use of global variables, okay? Because it's just a bad idea. We could do that, but then it becomes, kind of like using post increment as an operator to implement post increment as a function. So yes, so Kyle is correct that we could have used that approach, but I'm gonna make it more spelled out, to separate the right hand side from the left hand side. So the right hand side is evaluated here, and then whatever the value is, we're gonna use it to change whatever the left hand side is referring to. All right, so we're gonna initialize x with a particular value. I don't know, 23, let's say, and then we're gonna call postinc with the address of x, and that's it. All right. So, do we have any questions about the C code at this point, other than the indentation looks ugly? Are all the operators in the C code familiar? All right, I got some confirmations. I do not see anyone asking to clarify a specific operator. Okay, so we'll go ahead and proceed with this code. And with this particular program, you can go on with C or C++, because as I said, this is a this code only requires what is in C. It does not require the additional parts in C++. So it would compile in C. It would also compile in C++. I'm going to pick C because I'm just a C person, not a C++ person. Alright, so what we'll do is we're going to put a breakpoint here and then click debug. And then what we'll do is run the program. And then we'll single step it, okay? Single step, and we can print x. Not surprisingly, it has a value of 23, and then single step again. Now we're in the subroutine. Now, this is where things can get a little bit more interesting. It also relates to how you can write the code for today's lab. I'll talk more about that in just a little bit. So right now we have a parameter which is ptr, so I can print ptr. I know this is a little hard to see, but ptr, I will say this is really hard to see because it's a very dark thing, in over a dark background. Let me see if there's a way to change that. That should be something that's easy to change, but doesn't look like that. Oh, wait, we can do it on the other side too. So we can actually look at, oh, it doesn't show as a local variable. Let me single step into it. No, it won't show up here, darn it. Okay. All right, so what we can do is watch expressions. There we go. Okay, so we're gonna put ptr here as an expression to watch, and it doesn't show the value either. I do not like this. I'll just kind of say, okay, I can do this. Oh, that doesn't really help, does it? It shows a little bit, okay? It's basically an address, okay? The question is, whose address is this? You can see it, okay? All right, cool. So this is an address. So the question is, whose address is it? And you guys will all say, oh, it's the address of local variable x of main, right? It kind of makes sense? Okay, thank you. Okay, cool. Thank you. Thank you for the confirmation. But the point is, it is an address. And you guys can conduct this particular experiment on your own as well. And I might switch to a command line version of GDB, just so that we don't have to deal with the contrast issue, in the web browser. So now, GDB has a really cool feature called Backtrace, which is BT. So Backtrace allows you to see how you got here. So we are currently in postinc, and where we are currently located is always referred to as frame 0. And then whatever is the caller of the current call frame is always frame number 1, and then frame number 2 would be whatever is calling that. But since we are coming from main directly, so we can only go back one step. So what BT is helpful for is we can now say, oh, let's go back and go to frame 1, because by default we are in frame 0. So frame 1 is the caller of the current frame, and now we can say, okay, tell me what is x, because from the perspective of frame 1, which is inside main, x is defined as a local variable. So we say, oh, okay, x has a value of 23. We know that already, but we can also ask, what is the address of x? So I know it's really faint and hard to see, but you can see that it is the same thing as ptr. So ptr has exactly the same value as the address of X. So that's what we are passing into post inc over here. So if I want to continue to debug the program, I can say frame 0. We can getting back to where the execution point is right now, and then we can single step. So after we single step, okay, we are now expecting local variable x of main to be changed. Okay, it should be changed to 24, and this is before we even return from post inc. And using that trick, we can now say frame 1 print x, and sure enough, it is already 24. So this is how you can use GDB to understand how the C code is supposed to operate when we have pointers and we are passing the address of a local variable to a subroutine. So the subroutine has no visibility whatsoever of the local variable that belongs to another subroutine, but it's okay because it still has access to the local variable because we pass it by pointer, by address, into the subroutine. Alright, so now getting back to the assembly code, the question is how are we going to do this in assembly code? The one thing we are not going to do is the printf. So we forget about the printf, hello world. Well, we're not going to do that, okay, because the TTP ASM does not yet have any type of input-output that can print something out. So we cannot do that. But what we can do is the rest of the program. Alright, so let me stop the program execution from online GDB, and then at this point we're going to use a command line editor to edit the assembly code. There we go. Alright, so we're going to call this one, let me see, post inc. There we go. So post inc.ttp asm. I like to kind of use the extension TTP ASM just so that I can tell from the file extension that this is the source code in assembly for text toy processor. But it also serves a second purpose because the way I set up NVim or NeoVim in this case is it would recognize that particular extension and then it will load the correct syntax highlighting into the editor, which is kind of handy because now if I do something not so smart, it will highlight the entire line and say, hey, this is not right. This is not right. Okay, this is not actual code in TTP-ASM. Whereas if I do something correct, it won't highlight the entire line. So it's kind of handy, but you kind of have to know how to use Vim or VI to utilize this particular syntax highlighting tool. So I'm not trying to push VI, okay? I'm not trying to push VI. I'm just saying that for people who are using VI or Vim, the syntax highlighting is an option here that is specific to TTP ASM. Alright, so let's go ahead and get started. The first thing we want to do is a no-op and a JMPI to main. The reason why I do this is already explained earlier. So we have post inc, and then we have main over here. Main is going to end with halt. So you can see I'm just typing out the outline of the entire program first, and then I go back and backfill whatever I need to backfill. So for post inc, so we got a few things we need to take care of here. So I'm going to deal with main first because one question is how do we make these local variables? And this local variable does not have static in front of it. So what are the two types of local variables in C++? So this is a question directed to the class, and I want to see if you guys know there are two different types of local variables. I just mentioned one, and what is it and what is the other one? One is static, that is correct. That's the one that I just mentioned. And what is the other one? No. Const refers to the fact that we are not supposed to change it, but it does not say anything about the lifespan of a local variable. It is no. Okay, I see they didn't quite teach this concept in CISP310. It is auto, A-U-T-O, auto. So all auto does, yeah, I mean, who would have guessed? So what auto does is to emphasize that the local variable lives on the stack. So from the perspective of main, it's going to need that on the stack. Okay, so the local variable x of main is living on the stack. But main has nothing else. So the stack pointer would be pointing to local variable x after we are done initializing everything. So auto just assumes it's data type. Nope, nope. Auto refers to what we call a storage class, and the storage class in this case is stack instead of static. All right. I might need to have a few words with whoever is teaching CISP360 because this is I'm assuming they just make the assumption that everything is auto, which is correct. Okay, so if you don't say a single thing, it is automatically auto. You have to say static if you want the other kind of local variable. So from that perspective, perhaps it is not entirely necessary to talk about auto. Okay, a few years ago. Okay, very good. All right. Okay, that's I'm responding to Maddie's comment. I wish I could teach all of the classes, and I'm pretty sure some of you wish I would not be teaching all of the classes. But at least if I teach all of the classes, I can make assumptions that are actually valid. But if I am not teaching some of the classes, I can't really make some of the assumptions. Anyway, so we will first start with the initialization of the stack pointer. This is the lazy way to do it instead of using LDID 0. And then what we would need to do is a decrement D right away. Okay, so what this decrement D is doing is to reserve space for local variable x. So it's just a decrement. We are not storing anything into it, even though later on we would. But at this point, I'm just reserving the space. And right away, okay, at the exit point of the entire subroutine, I have an increment D to basically say D allocate space for local variable x. Now, somebody is going to point out, because I have had this conversation before already, somebody's going to point out and say, but we're going to halt right after the increment D. Whether we do the increment D or not really does not matter. Well, it doesn't matter from the perspective of whether the program is going to crash or not, but it does matter whether we are cleaning up after ourselves when this subroutine is done. So from that perspective, we need that increment D here in order for main to be considered correct. So there's a difference between what works and what is correct. And in this class, in all of the classes that I teach, works does not imply that it is correct. The other way around is usually true, but something that does work doesn't mean it is correct. It just means that in the very few instances, it might be working just fine, but it does not mean it will work in all cases. All right. All right, so there we go. We have some text traffic. I do want to point out the stack and the heap are not the same thing. The heap has no specific ordering of when you store something and when you retrieve that something. So the heap is an entirely random access from a certain perspective. Okay, when you allocate something versus when you deallocate something, that's entirely up to the logic of the program. It can look entirely random. Okay, but when you're talking about a stack, you don't have that option. Last in, first out, that's the only choice you have. So they are entirely different things. They usually belong to different region of the memory space allocated to a process also. So they can't even cross over to each other. Yep, they're entirely different. There's not much to compare between the heap versus the stack, actually. So there you have it. All right. Oh, one more point that is kind of important for some of you is an entire process has only one single heap, but one process can have multiple threads. Each thread has its own stack, but they do not have their own heap. So that means if you have a multi-threaded program, all the threads are really sharing exactly the same heap, which also means if the threads need to access the same kind of objects in the heap, you will have to practice, you have to make sure that you establish what we call critical sections, so that only one thread can have access to one thing at a time. But that's a topic that we are not going to talk about in this class, okay? But since somebody mentioned, the differences between the stack versus the heap, this is something that you might encounter in the future. So I'm not going to go on with that topic for at this point. All right, so now we have just allocated. So we have basically done line 19 here, which is to declare and also allocate the space for x. And then we also have the deallocation of x at the very end of main. So now we can say, okay, we need to store 23 into x. How do we do that? So this is also a good time to kind of give you guys a suggestion. Okay, it is just a suggestion. So as it turns out, a label can be defined to be any value. Some of you have learned that already when we did the absolute value homework assignment. So I can now say x is as a label is defined to be 0. So the question is, why is it defined to be 0? So I'm going to comment here so that you guys can actually refer back to why the label x has a value of 0. So I'm going to say the label x is representing the offset to find local variable x from relative to, okay, so this is better, relative to where the stack pointer points to. Okay, so if you think about the stack pointer as an anchoring point, okay, what label x is trying to represent is relative to where the stack pointer is pointing to. Where can I find x? Well, since in this case we don't have anything else on the stack from main's perspective, so where the stack pointer points to is where I can find x, and therefore the offset or the displacement is a 0 in this case. So now we're gonna do LDI a with 23. So this is the left-hand side of line 22. Now obviously the line numbers is referring to the C program on the left-hand side. So there we go. And now we have to find out, how do we compute the address of x? So you can say, but tag, the stack pointer has not moved, so we can just do something like this and we're done. So this is correct, okay? I would say this code is correct, but it doesn't really give you a general sense of how to access a local variable or a parameter, okay? So as it turns out, local variables versus parameters, they are kind of the same thing, even though they have some differences. And I'll tell you what the differences are right now. The differences are, if you're accessing a parameter, the initial value of a parameter is specified by the caller. But if you're accessing a local variable, the initial value of a local variable is undefined. Okay, so that's really the only main difference between the two. But the way you access those two is really kind of the same because they both live on the stack. And you can always compute the displacement from where the stack pointer points to either one. Okay, so the offset to a local variable and the offset to a parameter, they will be different. But the way you access both of them will be the same because they're both at a constant offset from where the stack pointer is pointing to. So I think that part is kind of important to understand. So what I'm teaching you here is not just a technique to access local variables, but also a technique to access parameters. All right. So if you remember from the last question of the lab on Tuesday, you remember that, hey, but this code does not even look like what tag, used in class. Well, that's because, once you understand how things are organized on the stack, there are different ways to get to the same thing. So the idea is the lab is giving you a different way to access the same thing. But that turns out to be the much more general method in order to access something on the stack. So I'm going to use that method over here. I cannot use A anymore because A already has the value of the right hand side of the assignment, but I can use register B or C. In this case, I'm going to use register B. So at this point, B is the offset to local variable X from the stack pointer. So everything is relative to the stack pointer. And then the next thing I'm going to do is to add D to B. So does anyone want to say what is B at this point? I am adding the offset from where the stack pointer points to locate X on the stack. And then I add the stack pointer to the offset. So what should it be at this point? Not exactly. So I mean after the add. After the add. So after the add operation, B would be the address of X. It is the address of X. Okay, so this is important. This is very, very important, is to differentiate between the stages, because the first stage is to load the offset, and then after we add the stack pointer to the offset, then we have the actual address. So the question is, what do we do next? Well, there's not much to do, because we now have the address of X in register B, so we just have to store whatever the value is on the right hand side to whatever B is pointing to, because B contains the address of what we call the left hand side of an assignment. So this will complete that particular operation. So this completes line, what was it, 22, and then we call the subroutine. Alright, so now we call the subroutine. So I'm gonna say call sub function. I keep using the term subroutine because that's how I learned these concepts, but these days they're called functions. Well, wow, big deal, right? So now we have to pass the parameter first. Okay, remember, if you have parameters, we have to push the parameter. I should say argument. Sorry. So we have if you have arguments when you're calling a subroutine, the arguments need to be pushed on the stack in reverse order. When I say reversed order, I mean the last argument has to be pushed first, which also means the first argument has to be pushed last. But in this case, it does not matter because we only got one argument. So there's no such thing as, oh, which one is first and which one is last? Well, it's both, right? The first one is the last one. All right, so how do we compute the address of X again? Now, I know some of you are saying, but Tech, we got it already. We don't have to recompute it. But just bear with me because I want to, make sure that, we understand how to compute it. So we're going to recompute it. Okay, so once again, X is offset to, A is offset to local variable X. And then we do the add. Okay, so now A is the address of X. And then what do? Now we have the argument. We just have to push it on the stack. So now we do a decrement D, stda. So we are basically pushing the address of X on the stack. And now we can push the return address on the stack. So once again, if you are pushing the return address on the stack, depending on when you do the decrement D, the .5 plus versus the .6 plus, is a slight difference, but you have to kind of remember which one it is. And then now we push that on the stack, which is stda. And now that we have pushed the argument and also the return address on the stack, it is time to actually go to the subroutine. So that part is done by JMPI to post inc. And when post inc comes back, we have one extra thing sitting on the stack, which is the argument. The argument should not be on the stack anymore because the subroutine is already done. So we have an increment D to get rid of the argument that is still sitting on the stack. The return address is already gone because we rely on the subroutine or the callee to get rid of the return address. So that would be this is all the code that we have from the perspective of the caller. So now let me go back to the text channel and see if we have any questions over there. Did we use that space The first decrement D, this question is coming from Terrence. The first decrement D is to reserve the space for local variable x. So in addition to local variable x, we also need the space for the argument and then the return address. So you can see a lot of stuff is living on the stack. And then Matty said we add D to A, then move where D is pointing to. In this case, yes, because in this case, the label x is simply a 0. But when we have more and more local variables, the label may not be 0 anymore. So the way we do the computation here to compute the address of a local variable and also a parameter is universal. This will work whether we have one single local variable or whether we have a bunch of local variables. And the worst thing we can do is to say, oh, if it is the last local variable, we use this method. If it is not the last local variable, use that method. That would not be very easy to remember. So I just want one universal method to access local variables as well as parameters. Alrighty, and Matty is still typing something, but I'm going to go back here and kind of explain what is on the stack from the perspective of post inc at the entry point of the subroutine. Oh, okay, all right. So from the perspective of post inc, there are two things we can expect on the stack. The high item, which is pushed first, is the argument. So in this case, from the perspective of post inc, the parameter is called Ptr. We have 3 decrement D and only 2 increment D in main, but that's fine because the callee is supposed to get rid of the return address. So that is why we only have 2 increment in main, but 3 decrements in main. All right, so from the perspective of post inc, okay, Ptr is at a higher location because it is pushed first, because that's the parameter, and then we can expect the return address to be here, and this is the agreement. Okay, the stack pointer should be pointing to the return address at the entry point of a callee. So we can already know exactly how to return, because when we return, we just have to do a LD B. We cannot use A because it's supposed to return the value, so we use return B and then D. Increment D to deallocate. This is answering Terrence's question of why we only have 2 increment in main, because the callee is responsible to get rid of the return address. And then we have a JMPB at the very end. So now that we have handled the returning part, so there are 2 returns that we have to think about here. Even though in C it's only one single return, in assembly language we have 2 concepts of returning, and they are quote-unquote orthogonal to each other. So when we look at line 14 in C, it's actually combining 2 things. It is specifying a return value and also returning control at the same time using the same statement. But in assembly code, it is 2 separate things. To specify a return value is to put something into register A, because according to the agreement between the caller and the callee for this particular architecture, the return value is supposed to live in register A. But then we also have these 3 statements here responsible for returning control from the callee back to the caller. So from the assembly language perspective, we have 2 separate steps to perform in order to perform one single return statement in C. So I hope that part is clear. All right, so now what do we do? Okay, so what we need to do is to do it step by step. Okay, so this is the right hand side. When you have an assignment statement, usually we want to evaluate the right hand side first, put the value of the right hand side to a particular register, and then compute the address specified by the left hand side. Shouldn't it be increment D? Yes, thank you. I totally messed up there. Thank you. So Dalton is correct. All right, so in order to make it easy to access the parameter, now I define a label called Ptr, and in this case it is at an offset of 1 because the return address itself is at an offset of 0, so Ptr is at an offset of 1 from where the stack pointer points to. So that's why I define Ptr to be 1. And with that, I can now use the symbolic name. I don't have to remember in my head of, oh, where is PTR? And okay, I know C is now pointing to where the stack pointer points to. I need to increment to get to that location. Nope, from here on, it's just a symbolic name. Okay, this makes it easier for a programmer to handle it because we don't have to track, okay, a particular floating register, to find out, okay, where is it pointing to now? Do we decrement to get to where we need to go, or do we increment to get to where we need to go? Nope. Now that we have one label defined to be the offset to the parameter PTR, we just refer to that name. So it's symbolic at this point. Okay, so what we need to do is to first dereference PTR. Okay, so we need to, there are a few steps to get to it, right? So the first thing is LDIA PTR. So A is offset to PTR. Now there's a notation to talk about this. Okay, I'm not really sure how comfortable you guys are about this. You can use this notation. Because it's actually legitimate in C and C++. You can actually perform pointer arithmetics, assuming we cast both the addresses into the address of a char. Doing the subtraction will simply give you the number of bytes between the address of PTR and where the stack pointer points to. So this is actually legitimate C code, assuming that we do the casting. And for those of you who say, but how do we know it is the right type? Well, now we know. All right. So the next thing we do is, okay, you have seen this already. We add a D to A. So now at this point, A is, okay, so I will do the entire calculation. So this was what this was the value in A before this operation. Okay, I'm just repeating what I have in the comment from the previous line. But then with this particular instruction, what are we doing? We are just adding D to the whole thing, right? So we are now saying, oh, let's go ahead and add D, which is casting to a char pointer first. We are doing this. Now, it doesn't, I mean, you don't have to be very good at math to understand that. Oh, but don't they just kind of cancel out? Yes, they do. So once they cancel out, okay, and I'm just lining up the comments here. So once they cancel out, what is in A? What is in A is really just the address of PTR. I hope this kind of helps to clarify, why this code works. Okay. So what do we do next? We got the address of PTR already. So when you look at this code here, do we want the address of PTR? No. We want PTR first, and then we want whatever PTR is pointing to. So we need an LD first. So we need an LDAA. So the A is now the dereference of whatever A used to have, which is the address of PTR. And if you were taught the dereference operator and the address of operator in CISP310, you know they kind of cancel out each other. Okay, one is taking the address of something, and the other one says, "Let me get to where you're pointing to." Well, they kind of cancel out. So A is now PTR itself. Okay, which by itself is also a pointer, but so at this point, it is important to differentiate between what is the value of PTR and what is the address of PTR. Okay, because they are both addresses, but they're different. Okay, because the address of PTR is right on top of the return address, but what PTR is pointing to, that's entirely up to what the caller specified the argument. So those two concepts are different. Okay, so I'm getting to the text channel right now. I'm confused how you got the address of P minus SP. Because this is where the PTR is located. Okay, so this, if I want to specify what this is going to be, this is the address of PTR, which is SP plus 1. Alright, so trying to wrap my head around this, I came up with, and is this right? I'm going to plug my headset and say rather than type. Okay, alright, I'll wait.
Can you hear me?
Yes.
Okay, so in the register bank, we have A through D,
Yep.
and they can basically hold 8 bits, right?
Each register can. Each register is a bit wide. Yes. Hmm.
Okay, so um, that can go up to 255, right?
That is correct. With 8 bits, they can specify values from 0 to 255. That is correct.
Okay, so we're using D to keep track of which place we are in the stack, which can go up to 255 because it has 8 bits.
Hmm.
And um, then we're assigning um, values for where that's pointing using the other registers in the place it's pointing to in ROM, right?
Not in round. We at this point
There's
we are
no
not.
RAM.
Yeah, exactly. Because we don't really see the ROM anymore. When you are actually writing code in TTP ASM, there's no awareness of the ROM anymore.
Okay. So anytime we have things in parentheses, that's actually saying the value, like whatever that is, that's the value that is in the RAM, not what the 8-bit register value is, right?
That is correct. That because okay, if you look at the code on line 14, okay, so the code on line 14 is establishing a path from register D to the A port of RAM. In other words, register D is specifying which location of RAM we are paying attention to. And then the D port of RAM, this is a RAM read operation, and then the D port of RAM is going to be connected to register B in the register bank. So we are taking whatever is at the location that register D is pointing to in RAM and then update register B with using that value. And this is why it is kind of important to first understand the architecture, because the architecture is what is dictating, how this LD operation on line 14 is going to take place, and it really explains it. Okay, when you look at the architecture and look at how the pathways, all the multiplexers and demultiplexers, which register is enabled, which one is not enabled. So when you look at all of those configurations, it really gives you the most complete, detailed, and low level explanation of what is really happening when an instruction
Yeah.
like line 14 executes. So,
It's funny though, neither one of them made sense to me at all until I had both components. Like
hmm
I've spent hours upon hours looking at the processor and going,
hmm
I this is so unbelievably frustrating. I don't know what's happening here. But once we started doing code,
hmm
then together, at least I'm able to make sense of the two. But
okay,
doing one without the other makes no sense at all.
okay. Um, so I guess you need a context. You need to contextualize. Yeah, I like those words. You need to contextualize what you're learning. So the more context you're provided with, the more neural pathways you can form in your head, so that you can quote unquote better understand the concept. Because now one thing triggers a whole bunch of other concepts, and that really is how we understand something. Is when you look at one concept, when you look at the word of one concept, your mind automatically fires up a whole bunch of other concepts that are related. That is how we understand something instead of memorizing, which means you're just finding one single thing. Okay, it lights up one single definition, and nothing else lights up. That would not be understanding. That would be memorization. So there you go. All right. So is that okay? I mean, Maddie, did I address what you were asking?
Yeah, well, and we were having a group on Tuesday,
Mm-hmm.
and I was trying to help um, others like understand um, that that which I figured out of the A, B, C, and D inside the register bank have 8 bits. and that um, how that connects with RAM and D and it being pointers. But I was like just barely wrapping my head around it. Um, and so probably not explaining what was in my head outside to other people very well.
That is a good exercise. In order for someone to gain a depth of understanding of a concept, trying to explain that concept to somebody else is actually a very, very helpful exercise. So, I just want to point that out because, I keep learning new things, when I teach classes. Not just this one, all the classes that I teach, every semester I learn something new. I shouldn't say learn something new, but I make a new connection between the concepts that I already understood from before. So there's always some new connections between concepts as we go. All right, that's a very good discussion. I like it. Um, okay, so getting back to, so is that okay?
Yep.
Okay, cool. So getting back to the text channel, there's no SUBI. SUBI is subtract immediate. Subtraction only can work between two registers. You cannot have one register and one constant. So what Jonathan was suggesting, which is sub A PTR, cannot work because we simply do not have the pathway to make that happen. And also in this case, it should not be subtract, it should be add. So you're looking for add I or add immediate, which does not exist. And once again, it is important to understand the architecture because when you look at the architecture, regardless of what the ROM content has, there's no pathway to make it happen. There's no way to take the D port of RAM and route it to one of the two inputs of the ALU. Such a path simply does not exist. So that makes the instruction entirely impossible. Okay, add I, with a register and the immediate value, it is just impossible. So this is okay. So I don't want to beat a dead horse that is already a hamburger on a grill, but um, but this is why I introduce the architecture because the architecture, even though there's a lot of details, okay, it's very tedious, but each component is not really super difficult to understand. Switches are the multiplexers and the demultiplexers. That's all they do. Okay, they are just like railroad switches. Okay, and now you're going from the one track to one option of the two tracks that's coming out of the switch. So multiplexers are just that. Registers, on the other hand, is like a D flip flop. Okay, you present what you wanted to remember, and then you have the enable, and then you use the clock as a timing of when to update. So the enable is kind of like saying who should update, and then the clock is saying when to update. So between those two, you have synchronization of the operations within the processor, and also you have control over who is actually going to pay attention and actually update. So that is why I talk about the architecture first, because without understanding the architecture first, then we'll all be writing code like what Jonathan just did. Okay, it is completely natural to do something like that, because in C and C++ and Java and JavaScript and Perl and Python, in all programming languages, all the HLLs, all the high level languages, the language, what you specify, the syntax dictates what is going to happen, right? It dictates what operation you want to perform. But in assembly language, the mnemonic is nothing more than just a handy way to specify an opcode. And the opcode is nothing more than just a very concise way to basically say, hey, we want to perform that bunch of microcode in the ROM to get something done. So, and then that in return is basically just pulling strings, to all of those individual components in the processor, in the architecture, to say, okay, you should configure this way, you should configure that way, and you should turn on, you should turn off, and so on. So when we have a rising edge clock, that is the moment when everything happens, right? Okay, this goes there, that goes over here, this will be remembered over there, da 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 da. Um, so but the bottom line is, okay, let me backtrack a few times. So the bottom line is, in assembly language programming, the language is nothing more than just a documentation tool. Okay, it cannot determine how things happen. Okay, only to a certain extent. But the limitation really is residing in the processor architecture itself. When you're doing C++ programming, all the high level languages, what you specify in syntax determines what is going to happen, and you have great flexibility in that case. So that's why the mindset of programming in assembly and the mindset of programming in a HLL, high level language, are completely different. They're kind of opposite directions of each other. So there you go. All right, so there are a few more comments here. That's why pets are great. Yes, I have two cats. I can totally agree. Okay.
I teach my pets whatever I'm learning at the time. I talk to
Oh,
them.
I see. Yeah, I talk to myself, so a little different over there. Um, can only subtract two registers. That is correct. So Alexander is correct about that. Alrighty. And then Ivan said, so to find PTR 1, do we count where the argument is on the stack? Is that why it is 1? That is correct. So, because whenever, from the perspective of PostInc, where is it supposed to find PTR? It is always 1 byte after where the stack pointer points to. Now, where the stack pointer points to, that can change, right? Because depending on who is calling PostInc and what where the stack pointer was already from the caller's perspective, the stack pointer can change. But the relative location of where you can find PTR does not change. That is a constant, and that's why it is represented here as a label. And then Jonathan asked about his question, whether that is right or not. Let me read that. So we should just see as not really sure about that. So those two instructions, okay, let me get back to here. So with these two, line 10 and line 11, together, all they do is to load the address of PTR into register A. That's all they do. So it has nothing to do with the return address. I'm not really sure why the return address is being pointed to by the parameter, because that's not happening. The return address has no one is pointing to the return address except for the stack pointer. The stack pointer is still pointing to the return address, but the parameter is not. All right, so we're gonna trace this, okay? Because when we trace this and we go through the analysis of the trace, things will look. It should become more clear, but you still need to jot down some notes. Okay, you're more than welcome to make a copy of the trace after this is all done. Just take a snapshot by making a copy of the assembler spreadsheet. Right at that time, then you have a snapshot of everything. Okay, the code, and also the trace. So once we get to that point, I'm going to pause a little bit so that you guys can all take a snapshot. But you still need time to jot down your notes, okay? Because what I'm doing right here is I'm statically explaining what each instruction is doing in the context of the original C code. It's very tedious, okay? There's a lot of stuff going on. I don't expect anyone to really take in everything, at this point. Okay, you probably want to either revisit this whole thing, without watching the video again, or you can watch the video again, and alongside you will be taking notes on your side, on the other side, because the way I write here is effective for myself. Doesn't mean that it's going to be effective for you. So you're going to have to take notes in a form that is effective for yourself and not for other people. Okay, so there's that. All right, so where are we? We are here. So now that, okay, let me just kind of comment here. This is the return code, return to caller code. So we are not really concerned about that part for now. All right, so where are we? We have PTR, but we don't want to add one to PTR. We want to add one to what PTR is pointing to, because there's a dereference right here. So that means we need one more LDAA. But I'm going to do it a little bit differently. I'm going to do LDBA. So this way, B is the dereference of PTR, which is exactly what we want before we add one to register B. So now we increment B so that register B finally has what the right hand side is specifying, on line 13 of the C code. Now we need to look at the left hand side of the assignment. Okay, where are we supposed to store that thing? You go like tech. Don't we know that already? We're supposed to store that to whatever PTR is pointing to. And can someone tell me which do we have a register with the value of PTR already at this point? And this is the other thing that is kind of unique to assembly language programming is you kind of have to mentally track, or you can use a piece of paper or comment to track what each register has at any particular time of the code. So if you look at my comments, okay, can someone identify which register has PTR in it? Register A is correct. Terrence is right, and so is Jonathan, and I think Vlad is typing the same thing. You can go ahead and finish it. I mean, just because you have the same answer as everybody else doesn't mean that you have to say, "Oh man, I wasn't the first one." It's okay. I mean, we can all type the right answer, in the text channel. Right. So now we need to store it back to the location. So now we do something like this, okay? Because we know that register A is PTR, so the referencing is storing to the location the PTR is pointing to. So this completes the entire thing, which is PTR gets whatever PTR has plus 1. Okay. So are we good so far? We are done with line 13 of the C code at this point. Are we good? All right. So now I'm going to look at line 14, which is the first thing we need to worry about on line 14 is not how to return to the caller, because that has to happen after we specify the return value. So we are much more concerned about the PTR, whatever PTR points to minus 1. You look at this code and go like, that sounds like a lot of stuff that we have done already. Do we know the value of whatever PTR is pointing to? Yes, we do, because we just store that value into whatever PTR is pointing to. So the value that we just stored to is still in register B. So register B has the current value of whatever PTR is pointing to. So that means if I want to subtract 1 from it, hey, that's easy. Just do a subtract 1 from register B. So now B has whatever PTR points to, the value that is pointed to by PTR minus 1. All right. But guess what? Register B is not the register to store the return value. Okay, fine. We'll burn 1 instruction to do that. Okay, so now A has, okay, this is supposed to be B. So now A has the correct return value. And then we just proceed to the code to return control to the caller, and we're all done. All right. So as much as when I explain this, I might sound confident this code is going to work. I really have no idea whether it's going to work or not, because I could have missed one single register, like mistyping a register D as a register B, like what I did earlier, and the whole program is not going to work. Sometimes it's actually a good thing, because I can then show you guys how to use the trace analyzer to debug your program. So in some way, sometimes I hope the code does not work, because then I can illustrate certain things that I find to be helpful. But other times, it's like, but that's going to take up some extra class time. So there we go. Submit, and then post inc.ttpasm. All right. So this is my auto magic script working. And then I need to find the assembler from the other tab, put it back into this window. Come on, put it here. There we go. Alright, so it is done. It's loading data, so it's... that doesn't look like the assembler. Or does it? Nope, it does not. It may be the wrong assembler. Okay, let me just force a refresh and see what it has now. Yep, okay, so you just need a refresh, that's all. Alright, so let's check out analysis. The analysis tab is really the trace analysis, and it is done computing. Alright, so the first few things we need to check is whether register D ends with a 0, because if register D ends up with anything other than a 0, that means we didn't quite balance the stack pointer, which is usually a bad sign. So register D did get back to 0, so we are good there. And then the next thing we want to check is what is the return value of post inc. The return value of post inc is in register A, so the last time we update register A is probably what we want to focus on, which is on this one here. A has the value of 17 in hexadecimal. So when you look at 17 in hexadecimal, the 7 is 7 times 1, but the 1 is 1 times 16, okay? Because each unit of digit 1 is representing 16, so that means we have 16 plus 7, which is 23, which is the correct answer. And then we also want to check what is being stored in local variable x. Local variable x has an address of ff in hexadecimal, and we can see the last value we stored into that location is 18, which is 24. So the post increment operation occurred correctly because it went from 17 to 18, because we can see how it was originally initialized to 17, and then the post inc subroutine incremented it to 18. So the assembler, the trace analyzer, is actually just a tool to help you analyze how each instruction operates, step by step. So I would definitely use the trace analyzer and combine that with the assembly code that we have already worked on, and on top of that, also correlate that with the original C code. So I would basically have a 3-window thing. Okay, open up the C code, open up the assembly code, and also look at the result of the trace and be able to go like, okay, this instruction is executing here in the trace, and I can now confirm what the comment is saying about blah blah blah. Okay, this register now has the address of blah. Okay, so I would definitely go through this at least once, step by step. I know how tedious that sounds, but as a 4-unit class with 3 units of lecture and 1 unit of lab, you're supposed to spend 13 hours per week on this class alone. So how are you going to spend 13 hours? This is how you do it. I'm not sure. Is it 13 hours? It's basically for each lecture hour, you're supposed to spend 2 additional hours to study and prep for the homework and whatnot. So I could be wrong with the 13 hours. That sounds kind of excessive, but you guys can do the arithmetics. All right, so we got some traffic in the text channel. All right. I'm still confused about the local variable storage. Okay, so the local variable storage is FF. Let me see. I'm trying to find a good way to illustrate it, and I think I have a way to do it. Okay, so I'm gonna use Joplin for that. All right, so the question is about the local variable. All right, so let's see. All right, so I'm gonna give you a table, okay, and I need to find out what columns I need. Okay, so I'm gonna just say stack content. All right, there we go. So that turns it into a table. So with a normal subroutine, with a normal function, the arguments would be sitting at the top of the stack. So this would be argument n, and then followed by argument n minus 1, and so on. And then at some point, you get down to argument 1 and then argument 0. And then below that would be the return address, because the return address is what the caller is going to set up last, okay? Because it's the last item to push, so that means, relative to all of the arguments, it will be the item that has the lowest address. So the return address is going to be here. Now, depending on whether the function, the callee, has local variables, this is where the local variables are supposed to go. So local var 0, local var 1, and so on. And then after you allocate for the very last local variable, so we'll call this local var m, this is where the stack pointer points to. So register D is supposed to point to that location. Alright, so I'm not sure whether this picture helps or not. Yes, so Terrence, you're correct that the local variable x is actually stored on the stack. So when did we store that in the TTP ASM code? That is done in main. So if you go back to the code in main, this is where we accomplish that. So line specifically line 38 is where we store 23, the value of 23, which is 17 in hexadecimal, into location FF. And let's see, FE is not the return address. FE is actually the argument that we are pushing when we call post inc. So that would make FD on the stack, in memory, to be the actual return address. And then Matty asks, one WTB a dynamic form that has 5 boxes, one for each register in the bank that shows the 8-bit, and then one for RAM that shows the stack. Want to buy? Okay, I see. You can use comments for that purpose, and that's kind of what I'm doing here with the comments, is to document what is in each register for each step. But to find out what is in a register backwards, you kind of have to look up quite a bit in order to find out, okay, so when was the last time we updated that register, and what was in the register the last time we updated it. So yeah, so I can see the value of a form, but at the same time it's going to be very tedious, because that form, you need a copy of that form for every single instruction that changes a register. So that can get very tedious really quick. You might want to use a different approach, which is to use a spreadsheet approach, because with a spreadsheet you can have one column designated to one of the registers. So that way, if a cell is empty, you just kind of keep looking up, which is visually easier to do. So that would be something you can do. Let's see. We store the value 23, which is 17, into register B. Nope. This is not how. It's not a CPR. Okay, so this is important. Not CPRBA. Okay, so there's a major difference between these two. And that's also why B is in parentheses. I did not have to make the syntax to use parentheses, but I make it use parentheses because we are dereferencing B in a store. But when we do a CPR, it is not dereferenced. This is also where the x86 instruction set is going to be super duper confusing, because they're all move instructions. So LD is a move, ST is a move, CPR is also a move. It's just that the the square brackets are at different places. Whether there's a square bracket and where the square bracket is at different places. So I chose to use entirely different mnemonics for the instructions, just so that we know one is load, one is store, and the other one is copy register. We are just copying the content of one register to another register. Alrighty. So that should address Terrence's question. and then STBA is storing the 8-bit value of A to the RAM at the location that B is pointing to. Yes, that is correct. We are treating B on line 38. We are treating B as a pointer into RAM and say, where are we supposed to store in RAM? B says, okay, I can point to that location. And what are we supposed to store into that location? Register A says, I got the content to store at that location. That's what line 38 is about. Yep, so Matty is correct. All right. Yeah, um, so to deepen your understanding of the difference between the ST instruction and the CPR instruction, I recommend going back to the computer architecture, to the TTP architecture in Logisim, and actually just look at the microcode for those two instructions, specifically STBA versus CPRBA, and specifically look at the pathways between the registers and RAM and whatnot, and look at the differences between those two instructions, and just jot down what you see as the difference. Um, I think that would be helpful, but that's just for people like myself. But I'm not sure for other people whether that's going to be useful or not. But this is why I have the entire architecture open sourced, is so that it's there's no mystery. Okay, supposedly there should be no mystery whatsoever, because you can drill everything down to the actual computer architecture, which has fairly simple components. It is tedious. Okay, I'm not saying it is not tedious. It is tedious. However, once you spend a few moments, maybe an hour or so, to kind of figure out what connects to what not and what each component is going to do and so on and so forth, everything is just like, oh, okay, I can figure this out. Yes, I can figure this out. Yes, I can figure this out. It's all about you figuring out what is happening when an instruction happens. And my job is to make it so that the architecture itself is quote unquote self-documenting. You will never find this kind of stuff with the x86 architecture, because it is not open sourced and it is far too complex for us to explain operations like what I just did, if we were to use the x86 architecture. But the TTP is simple enough where we can actually manage and figure out how things connect and why together in a certain configuration they get a certain thing done. All right. Okay, so I'm getting to the text channel. Just curious, would this be correct? PTR is x1 plus. Okay, so that reference is not okay, first of all, it is not. Because variable, okay, so let's check out what is on the stack. Okay, so I'm going to use Joplin for that purpose. So in this particular program, okay, and you guys kind of have to remember the context of this. Okay, so this is stack content and whos. Okay, so there we go. All right, so at the top location we have variable x of main. And then one location below that would be the first argument. So the first argument to post inc is, it has two names. Okay, there are two ways to specify it. The name known to the subroutine is PTR, but the value that we specify as PTR is the address of x. And this really belongs to the subroutine that we are calling, which is post inc. And then one byte below that is the return address. So this is the return address back to main, but it also belongs to post inc. It is specified by main, but it really is a part of the stack that post inc should have access to. So that's kind of how the stack looks like. So if you want to add one more column, which is where, okay, so now we can say this one is at location FF, this one is at location FE, and this one is at location FD. There we go. So I hope that helps a little bit, just kind of visualizing, what is on the stack and what is knowing the value of what is at each location of the stack is not enough. You kind of have to understand how that connects back to the concept in the C program itself. So I hope this helps, to kind of relate the content on the stack not only to the assembly code but also to the C code, so that we understand, oh, so the local variable of main has to be allocated first because main was called first. Okay, that's the first level of function call. And then when we call post inc, then we have to set up the argument and also push the return address. Now, if post inc has its own local variable, it would be below the return address. That is kind of how the stack is utilized in this specific program. So the next question is the top of the stack? that is cute. So the top of the stack is the return address. When at the entry point of the subroutine, this is actually quote unquote the top of the stack. The top of the stack refers to the very last item. The most recent item on the stack is the top of the stack, and this is the most recent item on the stack. Yes. No, 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 no. Don't use the word bottom. The lowest address, the lowest location. Because if you use the word bottom, then it kind of contradicts, intuitively contradicts the term top, which adds to more confusion. So the most recent item is at the lowest address in memory space. Yes. Yes. Yep, I know this part is counterintuitive, but it does come in very handy. Okay, because this way we can just go like, oh, this is where the stack pointer points to, and then these bytes, okay, on top, these 2 bytes, the stack pointer points to this point at the entry point of post inc, but then this byte is actually a part of the stack that post inc has access to. Even though it was not set up by post inc can make assumption and go like, yeah, I can assume this byte here is the return address, and I can also assume this byte over here is the argument on the stack, is the parameter on the stack. So numerically, the top would be the lowest number. Yes, Matty is correct. So the term, quote unquote, top of the stack, is basically referring to the most recent item on the stack. The way we organize the stack in all architectures, so this is not because tech thinks in a weird way. All architectures, would grow the stack downward. Okay, like this in this class. So in this context, the where the stack pointer points to is actually the most recent item on the stack. It would also be the lowest address compared to all the other things currently in use on the stack. I hope that kind of makes sense. Are we good so far? Because we are quickly running out of time. But before we conclude today's class, I want to kind of check, make sure my term is right. Abstract data type. All right. So abstract data type. Yep, they do refer to the top. Okay, similar to a stack of plates, adding or subtracting is only possible at the top. So yes, so the term top of the stack does refer to the most recent item of the stack. Yes, buffet plates. Yep, exactly. Yep. So if you think about, so visually it doesn't help us because visually the stack here is growing up. The very last item you push on the stack is actually physically at a higher location compared to the base of the stack. So the stack that we have is kind of looking at this, but upside down. I know this part is counterintuitive, but there's no easy way around this portion because that is how all architectures work. Okay, so if you look into any architecture, the x86, the ARM architecture, the AVR architecture, the PowerPC architecture, they all arrange the stack in this particular way. So there's no way around this one. And we add item from the top. Well, yes. Okay, yes. So Maddie is correct. So it depends on how you organize the spreadsheet. So the way I document in both the comments of my code and also in the pictures, I always document it, so that whatever appears to be, okay, let me go back to the place where so whatever appears to be on top is the higher address. Whatever appears to be at a lower address has the lower address. So the stack is going down in this particular way. This is just my convention, because most people associate, high address to be higher up. So I'm using that particular way of visually arranging things. So if you want to think in the opposite way, you kind of have to make your own diagram or change the diagram that I have. So I don't have a problem with including this code, and also I cannot archive this. Okay, there's no way for me to archive this as a file so that you can upload. So if you want a snapshot of the assembler at this point, you might want to head over to the assembler that I have been working with, and just click on file and then make a copy. So that way you can make a copy in your own folder with exactly the code that we talked about today, and also the trace already done. So this way you don't have to go through the trouble of going through collecting the trace and then uploading the trace and to the trace analyzer and stuff like that. So that is highly recommended. You might want to do it in the next, I guess, hour or so, because before I need to change the assembler. All right, so we have a lab today, and this lab is a little bit interesting because it's separated into two parts. The first part is something you have to turn in. It's just your kind of questions in Canvas that you have to turn in by 1:20 p.m. today. And then the second part is your submission of a program. So that part is actually due next Tuesday at 9 a.m. Okay, right before class. So it's due right before class next Tuesday. So you have a weekend to kind of work on it, because it might take you a little bit of time to kind of think about the concepts that we have learned today, and then apply that to the program that you're going to be writing over the weekend. So so let me point out where we are talking about here. So we are talking about function calls and function call program submission. So these two, the first one is what you need to turn in today by 1:20. This is just a quiz type of format, and then the other one is an assignment format where you have to turn in a file. So this is the one that has an access key, and I think the access key is frame. I could be wrong. Nope, it was swap. I was wrong. Okay, so swap is the access key of today's lab. Are there any questions about this? Okay. Yeah, frame was Tuesday. That's right. Yeah, this one was swap because guess what type of subroutine you'll be writing? It's a swap subroutine. Yep. And if you look at the swap subroutine, you will look at things and go like, oh, so that kind of resembles what we are talking about today, and that also resembles what we are talking about today. Yep, that was the intent of today's lecture. All right, so are there any questions I can answer before I sign off the voice channel? All right, so in main, instead of stda, could you use stdb? You mean in the assignment in the lab today? For the second decrement something. The one we did in class. Okay, so let me get back to that first. All right, so this is main. So which line are we talking about? We got one decrement on line 33, and that's for allocating for the space for local variable x. So line 46. And the suggestion is instead of stda, can we use stdb? Because b has the address of x already. The answer is yes. When I worked on line 43 and line 44, I think I did mention that we could have reused register B, but I said, just to make it clear, make it more clear, I'm recomputing the value of the address of x so that, the recomputation is local to the context of we need to push the address of x on the stack. So Ivan is correct. I could have saved myself some trouble by removing line 43 and line 44 and then change line 46, what is currently line 46, to use register B instead of register A. That is correct because register B still has the address of X, the last time we updated it. That is correct. Alrighty, so that is correct. Okay, good observation. Alright, so you guys got some work ahead of you, and I would before you even try to write the swap subroutine on your own over the weekend, I would definitely kind of go through the program that I did today, kind of refamiliarize yourself with all the concepts. What is on the stack, what register is playing what role in the code at which point of the code, and as Maddie suggested, the way I would do that is not to use a form. So I can show you, kind of what I would do if I were to try to create a program or to create a form to make it easier. Oh, that's not what I want to do. Come on, Office. I want a spreadsheet. There we go. All right. So the way I would do it is to use one column for the actual code. So the actual code is going to be, so the content of column A is exactly what you can copy and paste into the assembler. So that would be the actual code. And then the other columns, I would basically say what is in register A, what is in register B, C, and what is in register D. And then in one more column, I would track what is on the stack. Okay, so now, when you're tracking what is on the stack, then you have to decide whether it is going from left to right or right to left. Okay, in other words, if I have my approach to do the stack would be something like this. So I would say, main.x, which is, local variable x of main. So you can use different notations, but the idea is, I want to say, the main, the variable x of main is here, which is the bottom of the stack. This is the first thing I push on the stack. And then we have the argument, which is post inc. From the perspective of post inc, it is the ptr parameter. And then we have the return address on the stack. So I would use this particular order. It's easier this way because whatever you are pushing on the stack is always on the right hand side. And to me that makes sense. Okay, now obviously different people would look at this in a different way. So if you like to do it the opposite way, you just have to be consistent to do it the opposite way. So I would have these columns, and then with register A, you just have to remember what is in register A, for that line of code. So this way, if you're not doing something with a particular register, you just leave that cell empty. Then if you need to figure out what is in a particular register, you just have to kind of go up, to find out what was the last time that register was changed, and when it was changed, what was in that register at that time. And this method only works within a function, because once you call a function, all registers can be altered except for register D. We know how register D is supposed to be altered because we know that by the time it returns, the return address is deallocated. So that's the one thing that we know about register D. So that's kind of up to you to do this. Alright, so getting back to the text channel. Doesn't assembler do this? Do what? I'm not sure what this is referring to. If you're thinking about the assembler keeping track of what each register has, no, the assembler does not do that. The assembler has a very simple job to do, to convert mnemonics into opcodes and keep track of locations. But those locations are just the locations of the instructions. It doesn't care, doesn't know anything about the stack concept. the assembler has no concept whatsoever that there's a concept called stack. So yeah, there's no way you can rely on the assembler to do that. Alrighty. Cool. No more questions? Alright. So I'm going to start